Hello students, welcome back. Now let's go to section 2 and review the fundamental theorem of calculus. Here we go, the fundamental theorem of calculus. If f is a continuous real function defined in a closed interval ab, then there is a antiderivative function, capital F, in the same closed interval such that the integral a to b f of x dx is a net change of the antiderivative function. That is a short version of the fundamental theorem, and that's what we did in Calculus 1. In a little bit higher level, we'll consider the fundamental theorem in 3 parts. Number 1, the integral exists. Number 2, the antiderivative exists. Number 3, the integral is the net change. Number 1 is hardest to prove, and then number 2 and number 3. Number 3 is actually no big deal, as a matter of fact. So the net change theorem is actually the easiest part, the most trivial part of the fundamental theorem of calculus, to tell the truth. And also, it applies only to continuous function. Remember that? Now, how do you use it? Well, here are some applications. Calculating the definite integrals using the fundamental theorem of calculus. Find out the antiderivative function, capital F, and then plug in the top, plug in the bottom, subtract from the other. How about this example here? Well, expand this integrand and then get a bunch of power functions. Apply the power rule and you can get the antiderivative function, the indefinite integral. And then plug in the top, plug in the bottom, subtract from the other like this. Expand and then get the antiderivative like this. Plug in 1, plug in 0, subtract from the other, and that's it. That is the solution. How about this example? Well, this may be a bit difficult to integrand, but you can work it out. Separate the numerator, and then you can express it as a bunch of power functions added together, so you can apply the power rule. We get the antiderivatives. Alright, plug in the top, plug in the bottom, subtract from the other, and do your simplification. Up to here, it's indefinite integral or antidifferentiation. And then this bracket and top, bottom, I'm going to plug in the top and plug in the bottom and subtract from the other shortly. That's the shorthand of this expression. And then in these 3 lines, indeed, that's what I did. One more example. Okay, here's one more. Cosine squared can be rewritten as this using the power reduction formula, which is same as that. And then we can calculate the antiderivative like this. Antiderivative is done, so plug in the top, pi, plug in the bottom, 0, and subtract from the other, and we get the answer. See? The use of fundamental theorem of calculus to calculate the definite integral. But that's not the only application of the fundamental theorem of calculus. In Calculus 1, we considered this one as well. You can define a function using the definite integral and calculate its derivative. Basically, the integral is antiderivative. So derivative of integral is, roughly speaking, the derivative of the antiderivative, so we get the original integrand back. That's what it is. Define a function using the integral, take the derivative, and you get the original function back. Here, character t is just a dummy variable, you see? If you apply the fundamental theorem, what is this? Let's see, antiderivative is capital F, then this is capital, well, what's the top? What's the bottom? That's it, isn't it? That's what you get from the fundamental theorem. Do you agree? Instead of b, I have x, that's it. Now what if you have a little bit different character? Will that make any difference? No, it won't. Whatever it is, I'm going to plug in the top and plug in the bottom, subtract from the other. So whether you have t or s or now u or v or z, they don't matter. Eventually, we have to go back to the original. But then again, you see, I'm not looking for g of x, and I don't know what this capital F is. What I want is derivative. So from here, let's take the derivative. What is the derivative? Derivative of capital F of x, f prime of x, and then derivative of capital F of a. Is that it? Is that it? No, something's wrong. This is wrong. F of a here, which is coming from the fundamental theorem here. And what is the derivative? This is wrong because f of a is constant. You see? Once you have a function and take the derivative and then plug in the number, then you're going to get that. But this is not a function. I already plugged in x equal to a, so this is constant. So that derivative is 0. So derivative of the antiderivative, oh, we get the original function back. Okay? I don't need any of those. I did the complete proof, so that's it. So define a function using an integral, and then take the derivative, and you get the original integrand back. Whatever I start, whatever a value, it doesn't matter. a to x, whether it's 0 to x, 5 to x, negative square root of 17 to x, doesn't matter. That's just constant. We get just f of x. Whether this character is t, or s, or u, v, w, whatever, doesn't matter. You get this eventual character back. Now, that's just an intermediate part. This is a real deal. Now, previously, we had just a to x. I just had x. What if you have something like x squared? Or cosine of x, or whatever? In general, we have x expression in top, and also another x expression in bottom. In that case, what do you get? Well, the right-hand side. How? Here's the proof. Write it in terms of the fundamental theorem. We have antiderivative function capital F, so that plug in the top, plug in the bottom, subtract one from the other. That's the fundamental theorem. Agreed? The problem here is I can express it like that, but I don't know what is capital F. It could be really complicated, or maybe it doesn't have any nice algebraic form. I do know it exists, though. But then again, I'm not looking for this integral, remember? I'm looking for its derivative. So from here, take the derivative, then that's what you get. Derivative of the outer function, inside stay the same, and multiply the derivative of the inside. That's by the chain rule. Same here, by chain rule. And then what is capital F prime is not the antiderivative function, so this is small f. So small f of bx times b prime of x minus small f of ax times a prime of x. You have f of bx minus f of ax. That structure is coming from the fundamental theorem. And we have the multiplication b prime of x and a prime of x. They're coming from the chain rule. What is the most important topic in Calculus 1? Is chain rule. What is the second most important topic in Calculus 1? That's the fundamental theorem. Number 1 and number 2 put together. Okay, here's some applications. And this is a trivial application. 1 to x and this. So all I have to do is replace y by x, isn't it? Just plug in x there. That's it, but you can simplify. It's not necessary, but you can. By the way, this is one of those rare examples you can actually calculate the integral and then take the derivative again. I don't know why would anybody do this, but it is theoretically possible. Yeah, you can calculate the integral and then take the derivative back. Stupid, isn't it? Now, this kind of problem looks harder, but actually no, not really. It doesn't matter how complicated this is, because this u is just a variable, just dummy variable. So plug x equals to u and that's it. Maybe not. We have integral x to 2 instead of 1 to x. And this thing said we need integral a to x. How do I mend this problem? Well, that's how you do it. If you switch top and bottom, negative of the integral. So if you move backward, it's negative. So here we go. X to 2, change to 2x, and then we get negative sign. And then we can apply the derivative of the integral, plug x back inside u, that's it. Don't forget this negative sign, it came from the switching. Oops. Now here's something more challenging. How do you do that? Well, that's gonna be, no, not this. This. Plug in the top, plug in the bottom, and then multiply the derivative. Alright? Plug in the top expression like this, plug in the bottom expression like that, and then the derivatives, this and that, like this. Do not be intimidated by these kind of things. You don't have to take the antiderivative. It's just fundamental theorem plus chain rule problem. Also, do not take the derivative of this. You see, derivative of antiderivative. So you have to get this one back, more or less. But if you take another derivative here, then you're going over the second derivative. So taking the derivative of the sign, that's not going to give you any credit. Okay, time for some more. Well, we have some advanced problems here. I'll just give you some hint and then just move on. Let's see. Equation of the tangent line. Basically, we are looking for this. Find out y0 by plugging x equals to 1. And then take the derivative and plug in x equals to 1. Let's find out m. And then put all those in, and then you're going to get the answer. Okay, how to find out y0? Plug in x equals 1 directly here. And then you see that integral from 2 to 2, so that's 0. So it doesn't matter how complicated this is. Integral is going from 2 to 2, so integral is 0. Now, how about the derivative? Oh, that's basically what this is all about. Oh no, not this. You see, use this. Derivative, and then plug in x equals to what? X equals to 1, alright, plug in x equals to 1. That's my slope. Okay, y0 is 0, m is 3. Here's the solution. How about this? Believe it or not, this is a L'Hopital's rule problem. It's a 0 over 0 type limit. If you plug in x equals to 2, the denominator is 0, 4 minus 4. And the numerator here, integral 2 to 2. If you plug in x equals to 2 there, you'll see. So it's 0 over 0 type limit, so you can use L'Hopital's rule. Take the derivative of denominator, that's easy. Take the derivative of numerator, and that's what we were just discussing. This one here. So here's a sketch. Derivative of denominator is 2x. Derivative of numerator is just plugging in and then the derivative. That's it. And then plug in x equal to 2 and do some simplification, and there you go. So it's a L'Hopital's rule problem, believe it or not. Now, here's the hardest of the bunch. We're going to find out the inverse of increase and decrease. You're going to take the derivative, factor it, get all those critical numbers, and then do sign analysis. When it's plus, increasing. When it's minus, decreasing. Oh boy, that's got to be challenging. So let's take the derivative. And then the denominator is always plus, and you can factor the numerator to find out critical numbers. And then there they are. And then you can do the sign analysis, when increasing, when decreasing. And that's it. This diagram tells you everything. Here is the graph, by the way.